Hi, everybody. My name is Saporta, and I'm here to talk about a data-driven approach, modernizing, refactoring aging Java monoliths for Kubernetes in the cloud. So I want to start. Okay, I want to start with introducing the problem and talk about what is application modernization. So application modernization is a big deal, right? It's one of the largest undertakings that IT organizations are taking all over the world. And specifically, the biggest the IT organization, usually the more they have modernization projects, ongoing modernization projects, planned modernization projects. But modernization can mean a lot of different things to different people. To some, it may only mean updating infrastructure or containerization. For the most part, and what we want to focus on today is application modernization, which includes architecture modernization. So why do you think it's so important? Well, according to this report, it surveyed executives and asked them why did their company start modernization project. And the first thing everybody says is improve customer satisfaction. And then there is employee efficiency and satisfaction. And further down, we can see competitive pressure. And all of those kind of lead into wanting to innovate faster. And why don't companies innovate faster? What that kind of boils down to, what we have last year is technical debt. So although only 16% outright said technical debt, all of the others boil down to it. So what is technical debt? How does it apply here? Well, technical debt leads to longer test cycles, which leads to longer release cycles, which makes the organization unable to meet requirements, which will directly lead to poor customer and user experience. And customer and user experience are two different things, right? User experience is when a user is using the application, but customer experience may be that the customer has requested a feature or a bug fix, and it takes 6 months or maybe a year for that feature to appear. And that is poor customer satisfaction experience, sorry. And through all that, there's also the inability to efficiently use and ramp up developers, and developers feeling that they're spending all of their times on bugs and not enough on innovation. And it really brings the entire organization down. So we've established that these projects are very important, but this report shows us that most of them fail. About 80% of these modernization projects fail. And not only do they fail spectacularly. So they fail after a long period of time and after a lot of resources have been put into them. And that means that when it fails after a year and a half, a lot of these resources, a lot of money just goes down the drain. You're usually not left with like smaller victories, you just lost everything. So why do we think this happens? Well, a lot of these projects start out like this. So I have no idea who the people are in the picture, but basically an organization would say, we want to start looking into a modernization project, and they would usually contact a system integrator or an advisor, and they will come in with a few architects, and then they will all be joined in this meeting room, and they'll start talking about the project and saying, okay, we need 10 services or 20 services in the new architecture, and they'll start using the post-its like here to show you, well, different features that belong, or different capabilities that belong in each service. And most of this is based on what people remember. There might be this one person there using a laptop yelling out to everybody else, no, that is wrong, this feature belongs somewhere else. But usually still mostly based on hunches. And then once this, like usually week to couple of weeks initial phase ends, you're left with a plan. And in that plan, you usually have a POC to extract the first service. This will take 2 to 3 months. And after this POC is over, you have a go, no go. And in the go, no go, you decide whether it's worth to spend another year for a full project, or if you're cutting your losses and canceling the entire thing. And mind you, if you're cutting your losses, you've already lost 3 weeks, some money, 3 months, some money, and all that comes with it. And if you're pressing forward and you take in the year, usually the project won't be done in a year, and you will not necessarily have a lot to show for it. And then you have to make another decision: should I push another 6 months or another year to finish it, or am I just gonna abort right now? So why does it happen? It's happening because there are no tools for this. So it's just a bunch of people and a whiteboard. And the decisions are based on the hunches. And the existing technical debt is not directly addressed. And the long time every step of this process I just described takes makes every step harder, because things are still waiting. We're just accumulating. If it's not technical debt, it's definitely feature requests and customer requests and all of that. And it makes everything harder. So we're suggesting taking a look at a new methodology that is targeted directly at this process for developers, for architects, to use the right data and the right tools to transform monoliths into mini services or microservices through a repeatable process that takes kind of a fraction of the time that I just described. The idea here, there's acceleration and there's cost reduction, but the main idea is to reduce the risk. So if the POC takes, instead of 2 to 3 months, takes 2 to 3 days, then the go, no go that comes afterwards is much easier to do. And you have a lot more confidence that the project can and will succeed in reasonable time. So we split this process into two separate stages, phases. In the assessment phase, we have the assessment tool. So we have 2 phases and 2 tools for the job, just so we're still using always the right tool for the job, right? So the assessment phase, we want to examine the entire portfolio of a company organization and make smart decisions based on data on which applications should receive which treatment, what can we or should we modernize, what should we just re-platform, containerize, put it directly on the cloud. And then once we decide on the right applications that we will want to fully modernize and re-architect, then we will move on to the modernization tool. So let's focus first on assessment. So the idea here, as all others, is to use the right data to make smart decisions. Let's talk a bit about architectural technical debt. So when we talk about technical debt, it also can mean a lot of things. And sometimes we have these tools that tell us about code complexity or code smells, cyclomatic complexity, and point us into specific places in the code where there might be a problem. And although that is correct, it's not necessarily indicative that these problems are big inhibitors on the organization's ability to innovate. Architectural debt is really what we're trying to measure to help us understand how innovation is affected. So in the seminal paper from 2012, Nord et al., they brought forth a metric to help us measure architectural debt. So in this small snippet here, E stands for element. So the application is described as, let's say, a list of architectural elements. And each element, when we want to rewrite it or change it or create a new one, it's assigned a cost. And that cost is the sum of the costs of all other elements it interacts with. So here you see that it's split into 3 separate metrics. One is D. D is actually dependencies. So the amount of dependencies between 2 elements will decide how much it affects. So if there are no dependency between these 2 elements, then this entire thing amounts to 0, and we can move on to the next element. Then there is the cost of actually innovating that dependent element. And lastly, this is the propagation metric. So the propagation metric in the context of this article, it relates to kind of the average on a dependency between all elements in the system. Going forward, we usually use the term complexity to describe something very similar. We will get to that pretty soon. So the more a system is built loosely coupled elements, but then these loosely coupled elements will have very low propagation metric, and the probability that 2 elements will be dependent on one another also drops. But the more tightly coupled an application is, the more chance we have for all of this to kind of balloon and technical debt as a whole to be much more significant. One thing that this article didn't specify is what constitutes an architectural element. It uses it all the time, but it never says what it is. So we took a crack at it. And we thought, how do we define these elements? And we started with using the dependency graph of all classes within the application. So just imagine a graph and having edges between nodes, which are classes, if one class depends on another. And then we clustered using pretty standard clustering algorithm. We clustered these classes into communities, and we extracted some features from both the community graph and the original class graph. And we focused on longest paths in the graph and highest dependent list. So what we call fan out, right? If a specific node has a lot of neighbors. And also connectivity between communities, and specifically identifying what we call the common or infra community, which is a community that all other communities or most other communities relate to or depend on. And so you can say we really chose to define architectural element by not defining it, letting the graph of each application define it for us. It could be either a single class or a community, and all of these at once can be an architectural element. And so we took these applications that we had, our training set, and we asked their developers questions about how they perceive the technical debt of these applications. And we correlated that with these features we extracted that we just saw in the previous slide. And we found several of these metrics had a high correlation with the answers of the survey. And specifically, we saw that what we call risk, the high correlation between the number of dependents and the debt. So think of it as the risk that by changing class X, class Y, that doesn't seem to be related, would stop working as planned. And also correlation between the entanglement of the communities with the common or the infra community. We refer to that as complexity, and you can think of that as how much change do I have to introduce into the code to achieve a specific feature or bug fix. So as a developer, I think of it as when I first look at a bug and I have this thought that, yeah, it's just a couple of lines of code to fix it. And then I start doing it, and I started changing more and more and more and more. And not because anything broke, but just because I really underestimated how complex and how much I need to touch on different places. And I'm sure it happened to all developers in the audience. And then, kind of as a sanity check, and as expected, there's also correlation to the application size, because an application with 100 classes shouldn't have much technical debt, definitely not as much as application of 20,000 classes. So this kind of helps us balance and normalize all the data. If you're interested in that, we also published a blog post on this in Conveyor. Take a look if you like. So how does this look in practice? So what we're showing here, kind of two ways to look at the same data. So we're analyzing this application, and we see that, let's say 60-something% of every dollar spent goes to debt, to managing debt, to maintaining. So that means that about to spend $1 on innovation, you have to spend about $3 total, which is what we see on the right side. Right? Imagine it's 66%, and then obviously 2/3 of what you spend on debt, though you have to spend $3 to get $1 innovation. It's kind of tricky though, because if you were to lower this just by 10 cents, right? So let's say from 64% to around 50%, you think, well, just lowered it by 10 cents or by 14%. But basically what would mean that every $2 you will spend will now be spent on innovation. So by lowering the debt less than you would imagine, not to zero, you can really speed up your development process. We also talked about decision making, and decision making is, to make good decisions, you have to be kind of comparative. Because if you have one application, it tells you it has 60% debt, you don't really know what that means. But if you have two critical applications, and one of them has 30% debt and the other one has 60% debt, then you know where I should start with the one with the higher debt ratio, because by innovating debt, I will gain more faster. So in this graph, you see the average, which is dotted lines, and in each application, how it relates to that average in all three metrics: risk and complexity and the overall debt. Can also show this over time and even assign threshold, and you tell yourself, well, if my application reaches that threshold, I'm definitely going to have to innovate it. And lastly is also the refactoring effort report. I'm not going to go into that on this because it's part of the modernization platform. It's just another metric we show after we do the modernization phase to help you decide on the right way forward. So it really helps you to make this decision. So an application with a low refactoring effort and a low assessment debt level, you might just want to replatform it, or you might want to refactor it, but if the debt level is very high, you would want to refactor it anyway. And obviously to that, you have to also add the business priority, because if a key application, and it's a really big application, has low debt, you might still want to refactor it because it's really hurting you if it's your most critical business application. Let's move on to modernization phase. So our key goal here is to enable the modernization process. So we want to be practical, we want to keep everything moving, remove blockers as much as possible. To do that, we can't rely just on the static data, just on a dependency graph like we did in the assessment. We have to add some more data. And that data, which we collect during the phase co-learning, is the call tree of the application. So basically, we're collecting similar data of how classes relate to one another or how methods relate to one another, but during actual runtime. So now it's practical and less theoretical. And after we collect this data, we analyze it in the analysis algorithms, some based on UI, on heuristic and deterministic algorithms. And based on the initial analysis, the architect now can again sit and make database decisions on the output design of the microservice architecture. Then we have an automation process that can help you spit out really quickly and new minimum microservices and containerize them, and then immediately use them, test them on any cloud in any environment. So you notice I haven't talked at all about the data layer. And that's because usually when you read about microservices, one of the first things you read about is you have to have a separate data layer, a separate database for every microservice. And it's a good approach, although it's kind of an issue when you're refactoring an existing monolithic application. We find that it's kind of a disabler and not an enabler to the process because it's very risky, it's difficult to do, and you can't go back. If you moved your data from one database to another, you can't undo that. And even trying to do that, so I've done that multiple times in multiple projects. It's very difficult. You get data gaps and you try to recover from that, or maybe not all data is written. You're trying to duplicate it, to write to two simultaneously, and that's hard in its own right. So our approach is factor first and then split it. And we have the tools to do that, but still we want to focus first on refactoring, extracting services. So the key metric we use in the analysis process, both automatic and manual, is exclusivity. And exclusivity is simple enough. It means that an entity in the application only appears in a single service in the output architecture. And we measure this exclusivity on classes, on resources such as Bean, database tables, IO resources like files and sockets. And then our automatic analysis tries to optimize for all of that. There are some caveats like the trivial solutions, right? If we put each class in its own service, then everything is usually exclusive, but nobody wants that. And the monolith itself is also 100% exclusive because everything is just in one service because there is just one service. Nobody wants that either. And we also have a lot of other things to consider, like the architecture, number of hops. We don't want to call a service, which will call another service, which will call another service, which will call another service. That's not the architecture we're looking for. And there's common code to consider and the service sizes. So it's really very difficult for one algorithm to do that, all of that. And we haven't found the perfect algorithm. I don't think we ever will. It means that the key user here is the architect that needs to make a decision. So we bring a baseline and we bring a lot of data, and then there's a decision-making process. And I'm gonna skip ahead to how this looks in practice. So we've done the learning, we have collected all the data, and now we want to take a look at the baseline analysis that the algorithm suggested for us. And you can see on the left side, you have the metrics that we discussed, the resource exclusivity and the class exclusivity. And this is the service architecture. The lines point out which calls are made between services. So we now want to take a look at a specific service, in this case, the modified fulfillment service. And we want to look at its entry point. So an entry point is like an endpoint to the output service. So it can be an existing endpoint, like in this case, where the entry point is an endpoint of the original monolith, or it can be a new one, okay, we show very soon. And we can also make this look a bit nicer by hiding all the third-party functions that we collected. So let's deal with non-exclusive classes. In this case, we see the shipping service is a non-exclusive class in this service. So we want to check out why. And we see it appears in this service and also in the shipping price service. And just going just by the name, then we think it should probably be in the shipping price service. So we're going to see where it's called from in the modified fulfillment service. And we see that it's called using a Spring Bean. So we can mark that as a new entry point into the shipping service. And now our analysis runs again. And the result is that we have higher class exclusivity and lower resource exclusivity, which kind of demonstrates exactly what we were talking about, there being no perfect school school solution, right? So we'll take a look at resources next, and we see that there are multiple non-exclusive resources, specifically tables, database tables that we write to, and we want to take care of that. So we will take a look the same way and where this is called from the service, and we see that the sales order is called the line order table is called from the sale order hibernate proxy. And this is something I would not under any circumstance recommend to do in a real application. This is a demo application. It's just meant to look like an order management system. It's a skeleton application. So in a real application, you would find a better place to put an entry point. But for this, just humor me and we'll use this as an entry point and see how it affects the process. And we put it as an entry point to the order service and take a look how it affects. And we see we boosted the resource exclusivity a bit higher, again at the expense of the class exclusivity. So last thing I want to show is that we do have the tools to help make the decision regarding the data layer. So we looked at the order line, and the order line is now exclusive. It's only in one service, but we do see the payment info table in two services. And we can also look at this from the view of the order controller. And we see that the order controller uses all these 7 services. So when we go, after we extract this, when we go and we want to see, want to split the database, we know exactly what tables each service uses and if they're exclusive or not. So once all of this is done, we can go ahead and mark our services and go to service creation. And after that, there are some automation tools that will finish the job and extract the code directly into a new project that you can compile and test and containerize and put wherever you want. So just to sum up, what I really wanted to show is that this process, like any other big and important process, requires the right data and the right tool. And of course, it also needs the right architect for the job. Thank you very much for listening. You can also go here for a free trial. Okay, I see we have a couple of questions, so let me try to answer those. So I got a question: what are popular frameworks that can auto-refactor large, complex products code safely? And I'm not sure I understood the question. I will try to answer it to the best of my ability, but I'm not aware of frameworks that really automatically refactor large complex products. So our framework, the vfunction platform, allows you to do this, as I said, in an iterative process that can be repeatable and also reversible. So you can play around doing these operations as I did, like creating entry points, removing entry points, and always going back and fixing your architecture to best suit your needs. The second another question I got is, there was a tool that can do this automated. Developers won't be needed anymore. Okay, so we actually kind of get that a lot. It feels, although I really try hard for it not to feel like that, sometimes it feels like a lot of this is magic. Like there's this magical AI algorithm that does all the work, but it's not at all the case here. Nothing here is magic. It's just that it's a lot easier to do with the right tool. So there's still a lot of work to be done, but you're focused on the work that you need to do and not kind of going all over the place trying to find out what it is that you need to do. So this process still takes weeks or months, but it doesn't take years, and you have a lot more assurance that it will succeed in the end. I have a couple more questions. Is the automatic refactoring really works? Isn't that dangerous? You may end up fixing a bunch of stuff after the auto refactoring. What is your view on this? Okay, so there is no, what this platform does and all the things I talked about is extracting code from within the monolith. So the code doesn't change. So any bugs that were there will still be there, but we shouldn't be introducing new bugs. We're also not introducing any asynchronous operations. So everything we're introducing is REST-based and is still synchronous. So even if it's between services, it shouldn't change the behavior of the original application. So in that sense, if the code worked before, it should still be working. Next question, is the automatic refactor? Oh, I'm sorry, it's the same question, just wrote it twice. Okay, and another question I got was, what about front-end? I haven't talked about front-end at all. So front-end is kind of a different thing, because usually when modernizing an application, front-end modernization is a separate project, because you would usually keep the front-end as one front-end, or at least one infrastructure, and within that create sometimes micro front-ends. But this methodology is kind of focused on back-end and business logic. I don't see any more questions. So I would like to really thank everybody who listened to me. It was a great honor to talk J4K, and I wish you a pleasant conference, an interesting one. Thank you.